So the last of the field forces that we want to talk about is what's called Lorentz's force. It's the force on a moving charge in a magnetic field. Magnetic fields are produced by moving charges. When you move a charge, you produce a magnetic field, and I will go in a little more depth when when I talk about magnetic fields. But I want to throw this in there because we're talking about fields and forces. So I wanted to talk about this in this section. Okay? So what we've got a field, a magnetic field. Now, normally in magnetic fields, when we draw them, there's actually a couple of ways we can do them. They're a vector field, just like an electric field is a vector field. It's like a gravitational field is a vector field. So a magnetic field is a vector, and sometimes we can draw them like this, but most of the time we'll see them in text expressed in this form, either as a dot or an X. Okay, so when you're referring to it as a dot, that means the field is coming at you. Okay, in 3D. So that magnetic field line is coming in this direction. If it's an X, it's heading in this direction. It's heading into the board. Okay. The way that it normally we talk about it is that this is the tip of an arrow coming at you. So the direction is that tip of the arrow. It points in the direction of that field. Well, this is the tail of the arrow. It's the feathers of the arrow. So it's pointing into the board. Okay? And the reason we have to do this is that the Lorentz force is a three-dimensional force. It operates in all three dimensions, just in the same way torque operates in all three dimensions. When we talk about torque, we end up getting a torque vector that's perpendicular to both the radius and the force. So it's three-dimensional. The Lorentz force is a three-dimensional force. It does the same thing. It operates in all three dimensions. Okay? So when we talk about the Lorentz force, we're typically going to be talking about fields that come in or out of the board. Okay? So now I'm going to just go ahead and I'm going to draw fields that are going into the board. So now I've got this big unified magnetic field, not unified, constant magnetic field that's going into the board. Okay? Now, if a charge enters that field, it may experience force. Not always, but it may experience a force. So a charge, and let's pick an electron. Now let's pick a positron, which is a positively charged electron. That positron is now entering that field with a given amount of velocity. Okay? Well, Lorentz's force is saying that the force that object will experience, excuse me for 1 second, the force that charge experiences is proportional to the charge itself. It's proportional to the velocity of that charge, and it's proportional to the strength of the magnetic field. That all three of those things determine the size of that force. Now, we've got two vectors and we've got a scalar. The charge is a scalar. The velocity is a vector, the magnetic field is a vector. And we want to multiply them. Well, there's only two choices when multiplying vectors. It's either a cross product or a dot product. And we want a vector as a solution. So we're going to use a cross product. Okay? So it turns out that the Lorentz force, the equation for it, is QV velocity times the magnetic field. Okay, and I'm stating that V is velocity because if you remember when we talked about electric field, V also represented voltage, the change in potential. So I want to express it that way. So charge, velocity, magnetic field. Now this is a right-hand rule. It's a cross product. So when we're doing this, make sure you're using your right hand. And every time I demonstrate this, I always carry a piece of chalk around in my hand, because I have a bad memory for right and left hand until I broke my thumb. When I broke my thumb in my left hand, then I was like, oh, this side's broken, this side's not. Oh, right hand. Anyway, QV cross B. So what I want you to do is I want you to take your right hand and I want you to put it in the direction of Q and V. Okay? Q doesn't have a direction. It's a charge, but it's a positive charge. So that means if I'm multiplying a vector by a positive, it continues to move in that same direction. If I multiply that vector by a negative, that means that this vector would actually switch into the opposite direction. Okay, so QV. Now here's my hand in the direction of QV, but look how much rotation I have. All of these are possible directions in which I can turn my hand. So it's just a one-dimensional object here. It's going right in this direction. The other two dimensions are free to move in any way, shape, or form. Then what I'm going to do is I'm going to curl my fingers into the direction of the magnetic field. So if I curl my fingers in the direction of the magnetic field, which is now pointing into the board, I leave my thumb hanging out here because I have a weird thumb, but it always seems to hang out there. That thumb is actually pointing in the direction of the force. Okay? QVB, direction of the force. The force on a positive charge, a positron, moving in this direction, is in that direction. It points up. If you went back and you checked on that electron a little bit later, well, if it's moving in this direction and it's experiencing acceleration in this direction, you know it's going to experience something like that. Well, it turns out if you keep looking at the direction of that force, it's always pointing towards the center of that circle. It's centripetal. Okay? So this object is going to find itself moving in this circular pattern with the center pointing force. It's accelerating in the fact that it keeps on changing the direction of its velocity, but it's not accelerating in the fact that it changes the value of its velocity. So the really, really interesting thing about Lorentz's force, it never does any work. It's always pointing in this direction towards the center of a circle. It always forces that charged particle to move in a circle. Okay? So it'll never do work. It'll produce a force, but never do work. Okay? Now, if it was a negatively charged particle, what do you think it would happen? Well, we go QV, put our hands in here. There's the direction of the force. Right down this way. This object would rotate like this. Cool? That is Lorentz's force. It's a pretty cool force, and as a matter of fact, it's really important to the generation of electricity. Okay? Which is something we'll talk about another time. Cool? Alright, that's our field forces.